Okay, so from last time, last time we just introduced the artificial neural network, which was starting with inspiration from the neuron, and a lot of the work of the on artificial neural networks kind of sprung forth from work on the giant squid neuron, which is basically a gigantic neuron that in early days of electrophysiology provided a macroscopic entity on which to test the device properties of individual neurons. And although a lot of those properties inspired things that have been used in analog electronics, like the Schmidt trigger for hysteretic triggers with hysteresis, for a large part of up until very recently in the evolution of the artificial neural network, the focus has not been on the device properties as much as the networks of connections between these devices. But at least initially, then a single neuron was focused on as an interesting computational entity by itself. And we're now gradually getting back to the point where in spiking neural networks, people are actually adding in more physiological features of neurons. And we'll talk a little bit about that, I think, in the next lecture as we get to spiking neural networks, or at least introducing spiking neural networks and all the cool things that can happen with them. But for now, we're going to move today. I see a question, is that Nancy Lynch's work? So Nancy Lynch has a postdoc Nancy Lynch is a very well-known member of the computer science community, who's a member of the National Academy of Sciences and the National Academy of Engineering. She literally wrote the book on distributed algorithms. She has a postdoc in her lab who has become more interested in understanding distributed algorithms and distributed computation in populations of neurons. And I think so there are, and so that particular postdoc and actually a set of her grad students recently have been trying to sort of think about randomized algorithms from as like sort of Poisson processes, and you can actually think about neurons spiking in this framework as well. So then you can say that if I've got these activated units and I put them together, then how do I get these kind of distributed algorithms type things like winner take all and all of that. But and that certainly is one aspect of it. But even like far before that, spiking neural networks, and we'll talk about some of these frameworks, can be shown just to be able to do interesting, for example, I can build electronics that mimic the spiking characteristics of individual neurons. And if I wire them up in a certain type of way, then that aggregation, those wires together, can actually learn things in an unsupervised way, which again we'll get into next time around, without me doing anything. And that's just by ways of these spikes reconfiguring individual neurons in this spike timing dependent plasticity. So we'll get into all of that sort of stuff, but there's a lot of really cool stuff that's embracing the spike as an important part that has been left out of what we might otherwise call first generation artificial neural networks, where everything were these weighted combinations with heaviside step functions, to sort of second generation artificial networks where things started to take on analog values, and now in the spiking neural networks where we actually don't view them as taking on a value, but we actually view them as spiking in trains, and the information is in the trains. But that's kind of getting ahead of ourselves. So today we're just trying to get from the individual neuron into the network. And then the next time we'll try to then say, well, then once we've got these networks, what other cool properties could be added in there? All right, I saw at least one microphone go off mute. Is there a question? All right, then I'm just gonna hit the mute all for now, just to prevent any feedback or anything. Okay. All right, so so these are kind of our mimic of of neurons, and then so the kind of model that has been built up is that an individual neuron can be modeled like a set of inputs. So I'm going to just call this one like x sub 0 is just some constant term, and then some input x1 down through some input xn. And each one of these inputs goes through a weight. And so I'll call this weight W0, which is, we could also set equal to a variable called B for bias. And then X1 we'll call W1, all the way down into some weight Wn. All of these things get added together. So I'll draw them and coming into some sum junction and a signal flow diagram here. And then those then get passed through an activation function. And so I'm going to call this signal going into the activation function x bar. And x bar is just going to be the weighted average of the weights times the inputs. So this is x vector, so we'll call this is x vector. You can just call w vector. And then this activation function A of x bar then produces a scalar output y. And so this x hat, or not x hat, this x vector is this feature vector, which is sort of like all of the features of interest to us from our sensory system. Usually we think of this as kind of a coarsened representation of something out there in the world. And so these are bounding boxes from images, maybe the geometry of bounding boxes from images, or these are measures of odors from different odor components that possibly could be in a chemical combination, and so on. And then we view these weights here as kind of a feature of interest. We could view this as a prototype for a class of, say, signals of interest. And so this signal here is basically taking a dot product, or otherwise is, you could say W dot X if you like that notation, or this notation if you like the physicist Bra-Ket notation, or whatever you'd like. And so, we view dot products as an evaluation of similarity in alignment between two vectors. And so if two vectors are aligned, then this is a high number. And if two vectors are 90 degrees out of alignment, then this is a low vector. If two great vectors are 180 degrees out of alignment, it's a large vector, but it's negative. And so you can view this as kind of a measure of alignment. And then this activation function is then so then from there, the activation function represents some sort of critical amount of alignment for inclusion in the class. So you view the weight vector as kind of, this is our prototype. This is like if somebody asks, like, what does it mean to be a dog? Well, this is your cartoon dog. There may be no dogs in the world that look this way, but if I want to capture what it means to be a dog, then this is what I draw. And then so you put that in as your weight vector, and then you feed in a bunch of things that may or may not be dog-like. And the ones that have the best alignment with your dog prototype are the ones that will cause your activation function to activate. And the Y that comes out of here will end up being a high value if there's inclusion and a low value if there's not. And so your activation function, if it is a step function or something like that, it will then cause this to be 0 or 1. If it's a linear activation function, it might be a probability of inclusion into the class. And so there were comments earlier about, there's questions earlier about this soft max function that you hear a lot in these deep neural networks, and we'll get to what that even means to be a deep neural network. But this is sort of the degenerate form. A linear activation function is the degenerate form of a soft max. And so if you were to think about it, I have two options. You're either a dog or you're not a dog. And you could assign a probability to the two of those. Then you might say, you know, well, make a decision. Are you a dog or not? And you could just come out and say, I am a dog or I am not a dog. But you could then alternatively come out and say, well, there's a 90% chance I'm a dog and a 10% chance I'm not a dog. And so I just want those to add up to 1, and then that would be your soft max would provide you both of those outputs simultaneously. But in this case, we're just getting a 1 or a 0 out. So this is much more, if it's a hard activation function, it's much more like an actual kind of max. So that's kind of how these things will connect to things you may have heard of. But if we're just doing it, you know, nobody does machine learning with a single neuron. But if you were to do machine learning with a single neuron, then that's kind of how these things map up. So the Y can be, the question came in through the chat is Y going to be a decimal output? And the Y here could be 0 or 1, or it could be, you know, in an interval from, you know, whatever, it could be from -1 to 1 in the whole continuous interval. And this depends on the activation function. And so we are going to, if we use an activation of a heaviside step, which would be y is equal to f of x bar, which is equal to 1 if x bar is greater than or equal to 0, and 0 if x is less than 0, then in this case, y is going to be only 0 or 1, but you could choose other activation functions. I'm sorry, in the case of, so again, I want to be careful about, so softmax implies that you have multiple outputs. And so then you're assigning probabilities to every output, and then all of those add up to 1. In which case that would be a continuous output kind of for each one. That's what kind of makes it soft. So like if hard max or just max would give you a 1 in one of your outputs. So if you had a 5 different possible outputs and only one of them was 1 at the time, that would be kind of the hard max. And then the soft max is you're blending that across them so that they all add up to 1, but there's not necessarily a 0 in every other component. So if you're familiar with one-hot encodings, if you remember from like a digital logic class you may have taken, then the hard max is kind of a one-hot encoding across those outputs, and a soft max is like a blended version where it's like a mixed strategy across those outputs. But we'll get to that sort of stuff. So then we're just sticking to this one single one here, and the claim was that that this is identical. So maybe I'll just I'm just going to use this white space in the middle here, but there's no reason I'm putting this in the middle, so feel free to write on the next page and just save in the next page here. Is that, so the claim, oh, for some reason my screen broadcast says it stopped, so let me restart it. Apparently I have to rejoin from the tablet. Recording still seems to still be working though. Share content screen. All right, so think we're back up and running. Yeah, great. So the claim here is that this is identical for all intents and purposes to generalized linear modeling, or GLM, where the activation function is just a version of the so-called link function. So if you come from a statistics background, then a single neuron is just a single GLM. So where your X values are predictors, your Y value is a response variable, and you choose the activation function in order to match the response variable. And so different choices of activation functions correspond to different types of regression. So we were focusing on a simple task of binary classification, which is related to logistic, or can be related to logistic regression. Although the link function I would use for logistic regression is not a Heaviside step function. And then, so basically the thought is that you would have these features of interest to you, like X1, which could be, we used a car example before. So I was using a dog example. So maybe this is like fur color. And then X2, this feature might be number of legs. Those might be silly choices. And then the X0 component, which is that bias component, you could imagine that sort of projecting out this way, which is this, and we'll see how that works here in a second. But if you were to plot data on this plane where X0 is equal to 0, where you're just on the X1, X2 plane, then you have a bunch of data that are in the class and out of the class. And so let's say that that these data down here are just happen to be out of the class. And so I could call these data correspond to being, I'll say, O for out of the class. Well, O is not good because they look like dots. I'll just say A. So they're in class A and we're interested in class B. And then you happen to have another set of data that fortunately is over in a cloud over here, which we'll call class B. And these are all data, that you've got from training. So these are pre-labeled. And so the goal here is to say, given a bunch of labeled data, if I was then confronted with a fur color and a number of legs later, then could I label that data point based on the labels I've seen in the past? And so all I'm really trying to say here is, can I develop a mathematical function which separates this plane into anything above this line is a dog and anything below this line is not a dog? And so that is, if hopefully we can find such a dividing line like this. And the single neural network model, or the generalized linear model for this, basically ends up defining those weights, end up defining this line, and where the direction that is perpendicular to this line is in the same direction as the weight vector. And the position of the line, whether it's close to the axis or not, So I could say I'll say maybe the position here relates to this bias term. And so if I wanted to picture this in 3 space where I've got this x0 term, this bias term is a part of the vector, then this line here becomes a plane, which will happen to also intersect out here. And so as you move the bias term around, then you basically change where this plane is going to cut through the x1, x2 plane, and that is going to set this thing up here. So that's one way to kind of view this perspective. But the other thing, if you don't want to fold the bias into the feature vector, then you can just stick with this plane, and you can view the bias term as just moving this orange line back and forward, but in parallel slices. And so it can move in, it keeps its angle, but it moves closer to the origin or farther from the origin. And so our goal is to train both the bias term and the weight vector in order to get these things set up. And so if they're linearly separable, we would, so if we, under the assumption, so if linearly separable, then there is a simple algorithm that will work for the binary classification problem. And you just, 1, start with random weights, and then 2, update your weights so that the weight, any particular weight at the next time step of the iterative algorithm is the previous weight plus the dot product of the weight and I'll say this is input J vector minus Y and J, and this is output J scalar times the ith component of the jth input. And so we have here J inputs and J outputs, and that's our training data. And we run those inputs and outputs into this algorithm. And over time, if they're linearly separable, then this thing is guaranteed to converge to a weight vector that will separate them. And so that's great. But the question is, what if they're not linearly separable? And so that is where we start getting into thinking about, are there more complicated frameworks that we can put together that help to deal with this problem of not everything is linearly separable, even just for simple binary classification problems. And so even though my A's are down here, my B's are down here, for example, if I had a different structure here, like I might have a donut of A's with a donut hole of B's, then there's no way I can draw a line to separate A's versus B's. And so how do I deal with that? And so that's when solving that problem is when people started realizing that you could come up with interesting combinations of neurons that would provide additional ways to effectively manipulate your data to put them into a way that eventually some neuron in your collection would be able to do this more effectively. And so, so before I move to that, are there any questions about this idea of this linearly separable binary classification problem and how a single neuron can do this problem? Okay. Just for clarification, and this goes beyond single layer. This is one neuron. So all we've got is this single neuron up here. So the screen will stabilize. All we've got is this thing up here. So a single neuron, which is a single activation function, which is bringing in a weighted combination of inputs, produces a single output, and that is doing binary classification. So our then question is then why do we need to then increase to multiple neurons? And this part of the reason we do that is because the world, all binary classification problems cannot be solved through linear separation. Okay, so so one example of a solution to this are the so-called radial basis function neural networks. And these are in some ways also inspired by neuroscience. And I know this is probably very basic and a lot of review for many of you. And this is just kind of standard, chapter 1 machine learning stuff. But I just want to make sure everybody's on the same page. Got a mixture of different backgrounds here, and I think they're just kind of interesting topics as well. And so the base idea behind a radial basis function neural network is the thought is, well, what if I take that activation function and I tailor it for a particular nonlinear transformation, and then I put a bunch of them together, and then after transformation, combine all those together, and then maybe that will end up allowing me to do nonlinear classification. So the idea here is that I'm going to generate my first neural network here, so that I still have my inputs. So you can view these as, again, features if you like. And those inputs are now going to go into a set of these so-called radial basis functions, which I will explain here in a second. And then those radial basis functions all then sum up together. One big sum junction, and then that comes out. And so, and then this, by the way, can be a weighted average. So you can imagine these all coming together with a bunch of weights here. Now, and then these radial basis functions are sometimes called receptive units or receptive field units. So what the heck does that mean? Well, the idea here is a radial basis function can be a function like, you basically think of this as a nonlinear activation function. Maybe that's one way to view it, but a radial basis function can be viewed as a scaled difference between a feature vector and I should have drawn that each one of these features is going to go in to every function. So these aren't meant to just look like an input layer. So so just all of these x's. So just picture all of those x's going into all of those radial basis functions. And then the radial basis function, say Ri of the feature vector. So each one of these, this could be R1, this could be R2, this could be R3, this could be Rn. Each one of these radial basis functions is going to be, I'll say a function here, and this function could be, this function could be Gaussian, it could be logistic, it's some nonlinear transformation of a distance between the feature vector and some center, which is specific to that radial basis function. And so this here could be Euclidean. It could be some weighted Mahalanobis distance, etc. So it's just some, we'll say, norm or distance. It could be squared, it could be an L1 norm or whatever. But these centers are going to be an important thing here. So basically what each one of these, what you view as the output of each one of these radial basis functions is how much does the feature vector agree with the particular center point that this radial basis function corresponds to in the space. And so if you have your your x1, x2 feature space, then you're basically saying that for radial basis function 1, there is a center that is just for that radial basis function, that if you happen to be right at that center, then this radial basis function is going to give you a very high value. But as you move away from that center, then this radial basis function is going to fall off. And there's going to be another radial basis function nearby, and it will also have a decay around it. And the goal is to have these overlap some. And I'll call them kernels. And so those of you familiar with like convolutional neural nets, which we'll talk about here in a second, this is sort of related to that idea as well, is that each of these radial basis functions kind of focuses on a particular area, and it then amplifies things that fall into that area. But if you have a vector that is far away from that area, then that particular output is not going to be very high. And so what you're training here is we train, try a different color here. So we train both the weights and the centers. And so I'll say the weights, for simplicity, we'll put them inside this sum, and then the centers we put inside the radial basis functions. And so it's an expansion. So you go from, you now have a much more refined representation, because you are, because now you're training for, let's say you've got a certain number of feature vectors. You inside the network now, you've got more stuff to train. But what that additional flexibility gives you is it basically reflects that what you're doing is a nonlinear transformation on the input data, that hopefully after you go through the effort of doing that transformation here, then when you linearly combine them back here, then that thing that comes out may actually now say, for example, if you're interested in a classification problem, you might now be able to use linear separation. So it may be that for a binary classification problem, the features coming in were not linearly separable. But this nonlinear combination here allows you to reshape the feature space, so that hopefully after the reshaped feature space, then you end up getting something that comes out that, with the different combinations of weights, allows you to again be linearly separable. So that's one of the benefits of having multiple neurons, is it allows for you to start approximating these nonlinear transformations of the data that hopefully make them more statistically tractable downstream. And so this is just one, I'm just trying to motivate that. And so radial basis functions are commonly used, as I'm saying, they're for function approximation. So, you know, time series prediction, finding deterministic patterns in chaotic data, nonlinear classification. So I'll maybe put that in here, nonlinear classification. And other such things. So we add a little bit of nonlinearity. We were taking a linear combination. It's still going to be, when we are taking a linear combination of radial basis functions, it's still going to be nonlinear. Well, the local combination here is a linear combination, but the whole network is nonlinear because you've added these nonlinear components out front. So yes, you view this whole thing as a nonlinear. If you view it as a regression, this is a nonlinear regression, sure. And yes, you can put radial basis functions inside traditional artificial neural networks. Plenty of people do. So these is just one of the things in the toolbox of the machine learning or artificial neural network. It's just one of the sets that you have when you're doing machine learning with artificial neural networks, or these radial basis function neural networks, or you can shorten that to RBFNN. All right, so that I just wanted to bring that up to motivate the power of networks. Now, I would say that the more common network that you are going to see relates to a kind of simpler framework, or I guess a more direct expansion of the single neuron that we've been talking about, which is the so-called multi-layer perceptron. And so we can view this as a network of, I'll say, single layer or even single neuron perceptrons. And the key characteristic here is that it is, quote, feed forward. And so the idea here is that you have your inputs, just like we've been writing out here, and we can feed them into neurons like the artificial neurons that we've been working with. And we can imagine this mess of connections where all of the inputs can connect to all of the other. So we have all of our inputs and they can connect to these neurons, but then you can imagine that then these neurons can actually connect to additional neurons. And those additional neurons can attach to additional neurons until eventually you have some outputs, and you could have multiple outputs. And so I'm just going to sort of abbreviate, and hopefully you can imagine a mess of neurons connected to other neurons, but all moving, and they don't necessarily have to have the same cardinality of inputs and outputs, but you know, I'll say YM maybe. So all moving from left to right. And so the key point here is we have no connections that go backwards. We have no neurons like that are here that end up connecting to neurons that are back here. Everything moves from left to right. And that is, and so you've got a layer connects to a layer, connects to a layer, connects to the output. So inputs, layers, outputs. And so we can view these internal portions here as a so-called, as hidden layers. And then we can these kind of more conventional neurons that like make the decisions at the end, you can view as output layers or the output layer. And then you've got this input layer over here. And a deep neural network is basically one that has multiple hidden layers. And so a deep neural network is sort of capitalizing on this idea that you introduce variables inside the neural network. It doesn't actually have to be very deep. It just sort of has to have some structure on the inside. So a deep neural network has hidden layers. I mean, I think when I first learned about deep neural networks and I heard the term deep, I just thought, well, maybe if it had 5 hidden layers, it would be shallow, and if it had 50 hidden layers, finally we're at deep. And I guess it was very disappointing to me at that point in my career to find out that, well, deep can be very shallow. But the point here is that I guess I should mention that there is this thing called the Universal Approximation Theorem, which, make sure I spell the name correctly here, which was introduced by George Cybenko. And the UAT basically says that under some weak assumptions, anything you can do with a deep neural network, you can do with a single layer. So there is nothing special about what's possible with adding hidden layers. But because any problem that any function that you can approximate, so I guess I should write that here, any function, I'd say under mild conditions, can be approximated with a single layer but that single layer has to be, in order for you to approximate any function, and the kind of the growth of how wide that layer is, so how many neurons have to be in that layer, it's exponential growth. And so it's just not really tractable to implement. And I say under mild conditions, so yes, there's a proof of this. So if you were to look up the UAT, so you can go and just, if you were to Google, for example, the Universal Approximation Theorem, then you'd find that this is a well-known result that, that again, a single layer is enough. But there's two problems with a single layer. One, that in order for you to do that approximation for an arbitrary sort of set of functions, there's no way you can kind of bound the size of that layer. So it may be that that layer becomes just gigantic, it becomes extremely wide. And the other thing, which practically tends to be very important, is we're not actually saying that that single layer is somehow easy to train. So it might be that it's so big and it's so wide, and that you might not be able to use these cool techniques that I'm about to introduce, like backpropagation and things like that, effectively with a single layer. So the part of the reason people have gone to deep neural networks is they're basically saying that although we can approximate any, and when I say mild conditions, under like, I mean that it's not every function, but if the function is It meets, it has certain Lipschitz conditions and so on and so forth. And you can look up the exact conditions if you were to look up the UAT. But basically, almost any function that we practically would care about in a machine learning or an engineering application can be approximated with a single layer. And that's what the UAT is saying. But you may need a huge number of neurons in that layer, and you may have a hard time actually solving for the optimal weights for that approximation. So you may not find it. Finding it, it may be that there exists some weights out there that approximate with a single layer, but actually finding that existential witness is going to be very difficult for you to do. And so that's part of the reason why deep neural networks were introduced, is that they make it easier for us to exploit the representational space of a neural network, and they can have sort of bounded width. And that bounded width still allows us, through the interconnection inside these hidden layers, that actually provides us the ability to have a lot of expressivity, a lot of expressiveness without getting extremely wide. And so, so that's the kind of the real insight behind this wide structure of these neural networks, as they're more trainable, and they are have a, I would say, more practical bounds on spatial complexity. Now, the other note that I would just want to make here, and when talking about these feed-forward networks, is that the activation function, so this is separate from the Universal Approximation Theorem, but the activation functions here are going to be nonlinear, because if you had, or at least there's going to be a lot of nonlinear activation functions, because if you had linear activation functions, then the entire network, the entire feed-forward network, could be compressed into a single layer itself. And so there doesn't make a lot of sense to create a bunch of linear combinations of linear combinations, because linear combinations of linear combinations are just linear combinations. And so if you have, so just kind of a minor note, is that if all activation functions are linear, the MLP can be replaced with SLP. And so because of that, as a consequence, then the activation functions will have nonlinearities. Otherwise, it's just no fun. It's just extra work. So that's the motivation behind the MLP. And so then the question then is, how the heck do we train this? All right, so I see two questions here. So the earlier one here, or the later one, is a little smaller. So, but then what is it? So the UAT says that even with nonlinear activation functions, then the UAT is saying that any function can be approximated with a single layer. So, so the UAT isn't about compressing a multi-layer into a single layer. The UAT is about, do you need a multi-layer? And the UAT would say, technically, you don't need a multi-layer. A single layer is enough. And you might need to use nonlinear activation functions and all of those sorts of things, but you don't need all this extra complexity. A single layer is fine. And so these two things, now, if you happen to have a multi-layer perceptron and everything has linear activation functions, then what I'm saying is that you're just doing extra work. You're just kind of you're basically doing coordinate transforms that are all reversible, and you're just kind of doing them for fun, when you could just compress them all together and just have a single layer that gets you the same mapping from input to output. So The UAT is a more general result saying, do you ever need a multi-layer perceptron? No, you don't. And then the side note is, if you do have an MLP and you've had all linear activation functions, then you may as well just replace it with an SLP, because there's no benefit. So you don't get any benefit of having an MLP with all linear activation functions, but you do get a benefit of having an MLP with nonlinear activation functions, because it might be more trainable and it might have better spatial complexity. And then I say, based on what I've understood in regression, we're looking for an ANN to fit a curve. We're an ANN to fit a curve of the training samples. And in classification, we're looking for a curve which best separates the two. So what part in the model structure decides whether an ANN is trained for fitting the data or separating it? So fitting the data and separating it are actually kind of two sides of the same coin. And so in a linear regression, you are trying to find kind of the best line which fits a bunch of data. And in a classification problem, you are effectively using that line in order to define what's above and what's below. And so I guess if you imagined you've got a data set which has two big clusters, one here and one here, and you have an independent variable that's underneath those two clusters, then what maybe I should just draw that. If this is confusing, then, so if I have an independent variable here, so this is my independent variable, and my independent variable, let's say, it swings from low points to high points. But if that just happens to be that I've got that most of these points are below some line, and most of these points are above that line, and the points that are below that line corresponding to low points of my independent variable, and the points that are above that line corresponds to high points of my independent variable, a linear regression is basically going to fit a line through here. And that line is going to capture this slant that says that as your independent variable gets higher, then your dependent variable also gets higher. And what a classification does is it basically sets a threshold which says that if you then take a new data point, which is, say, here, and you then run it through your linear model, if your linear model comes and gives you a value which is above this threshold, then we can view this point as being a part of this class. Otherwise, if it's below that, we can view this point as being part of this class. And so a classification problem, you can kind of view as underneath the scenes, a linear regression plus a threshold. And so the two things are kind of identical. And so choosing your activation function is kind of choosing whether you're letting the linear regression pass on through, or you're thresholding it and turning it into classes. So are there more questions about this basic idea? Our next topic is how we train these multi-layer perceptrons. So just want to make sure I cover all of these things about the statistics of these. All right. Great. Okay, so then the question then here is, how do we train these multi-layer perceptrons? So we had this cute little heuristic that worked for the single neuron. And do we have something that we can expand to this other level here? And so that brings us into this kind of MLP supervised learning. I put quotes around supervised. I should probably put quotes around learning as well, because like the average person, what neural networks do may not view as like learning. It's not like they are learning to generalize from picking up a cup of coffee to throwing a baseball or something like that. They're just fitting, but that's the term we use. And so the basic tool that has been adopted that now has even been extended into spiking neural networks is so-called backpropagation. And again, apologize for the review for some of you on this, but just want to sort of make sure that we understand where this comes from and how it relates to the network structure. And so our problem is, for every input in our training set, for example, X vector, there is an output, we'll say an observed output Y, or maybe desired is another good term instead of observed. And our goal is to choose these neural network weights to ensure Y hat is close to Y, where this here is the output of the neural network for the given input. And just as a pause, these multi-layer networks, and so I talked about radial basis functions and how they have these receptive fields, and those were inspired by realizing that there are in the electrophysiology of how real neural networks work, there are receptive fields where these, in these receptive fields, you find that as you say, move towards certain patterns, say in the visual sensory space, and they move away from them, then you get an increase in activity that decreases as you move away from these kind of kernel objects. And it's not like it just gets stronger and stronger, like it really does seem like it's a distance. And so these radial basis functions were inspired by looking at the real response to real neural networks. And a popular multi-layer perceptron that we can talk more about is the convolutional neural network. And so backpropagation is one of the things that's used to train the convolutional neural network. And so so you can imagine, you can imagine structuring a multi-layer perceptron so that you have maybe a lot of neurons, say this is looking at an image. And so you could imagine that you could break the image up into pieces, and each piece you could break up into little pieces, and those little pieces might be individual pixels, for example. And so each one of those little pixels could be tied to a kind of input layer. And then and then if I view this group of these pixels, you can view those as getting aggregated is a kind of super pixel that would be the input for the next layer. And so you could imagine then that this somehow this one group here gets aggregated somehow to a single point, and then that single point becomes the input to the next layer of your neural network. And so there are a bunch of different ways to aggregate across those. And so so you can view these points as a so-called pool. And so each one of them is like a neuron that has an output. And you might take the neuron that has the largest output, in which case you would take the maximum of the pool, and that's so-called max pooling. And so there are these different ways of structuring your neural networks in order to generate these multi-layer perceptrons, and so or these multi-layer neural networks. And so you say, well, how the heck do I come up with these? You don't always just start with a general topology like the one that I kind of drew here. You might actually start with a constrained topology, and that's what the convolutional neural network is it is a constrained topology that basically starts from a very high resolution view of the world, where you've got a bunch of neurons looking at individual pixels, and then groups of them vote on kind of a super pixel, and then that becomes a coarsened view of the world, and then that coarsened view of the world goes through that again and again and again, and that's the so-called convolutional neural network. And it's called the convolutional neural network because of its similarity to a mathematical function called a convolution, which if you take signal processing courses, you'd be very familiar with. But still the question will be, how do you train these weights? So you've made the topological decision of what links to include, but then what's the best way to choose these weights? And so how do we choose the weights on one layer and then use that to help us choose the weights on another layer, and so on? And that's where this backpropagation comes up. All right, so that's our goal, is to choose these weights. And so how do we do that? So we are going to use a so-called loss function, which is an optimization objective. And our goal here is to minimize the difference between the neural network approximation y hat and actual outputs y for the same input. And so a easy loss function to use is just a quadratic loss function. So I can say, let's say there's E is my loss function, and I'm going to say maybe it's 1/2 y hat minus y squared. And, or you could imagine this could be, so I'll use that to be simple, but you could imagine like 1/2n, the sum of, some dimension equal 1 to n of y hat d minus yd squared. So you can think of this first version, if you'd like to, you can think of this in terms of a norm, in which case this norm might be kind of written down here, where these are the individual dimensions of a vector. But we're just going to keep it simple and think about, what if we had a scalar output? And so I would like to bring the difference between my scalar output and my approximation of the scalar output as small as possible. So I'm going to minimize loss. So we want to minimize this. Where this here is our loss. And so how the heck do we then choose weights that you're guaranteed, or at least move toward minimizing this thing? And so what we would like to do is try, we know for a quadratic cost function that gradient descent maybe makes sense. And so you might imagine that I'd say, well, let's say this is my collection of weights in the neural network. And so this collection of weights, we just iterate from one time point to the next by doing this gradient step, where we have a so-called learning rate, which is just a kind of step size. And we have a gradient of loss function with respect to all of the weights. So that makes sense in principle, but how do we calculate this gradient? We've got potentially millions of weights. So an image has, if you think about it, a 4K image or even an HD image, got a whole lot of pixels, and each one of those pixels might, unless you do some coarsening, each one of those pixels might be connected to a neuron. So you're going to have one neuron per pixel, and then that's just at the input. And then as you get all the hidden layers, then you've got even more of those. So you could have millions of these weights. And so how the heck are we going to calculate this gradient for these millions of weights? And so, so then we just say, well, let's think about this, and we're going to say, well, we're going to say, let's say what does the partial derivative of our loss function look like with respect to an individual weight? And so that is W subscript I subscript J superscript K. And so what are these things? So this down here, where I'm saying W I J K is the weight on output I in the K-1 layer to node or neuron J in the K layer. So it's a way of, I can index all of the weights in this way. And so how do I calculate this thing right here? And that's where some clever computer scientist remembered their high school calculus and realized that the chain rule makes this a much, much simpler problem. And so backpropagation is all sort of based on the chain rule from calculus. And so if you recall, the output, so I'll say, I'm going to say the output yjk. So this is the jth neuron, or the jth output in the kth layer of the neural network, is going to be equal to the activation function, jk, for that neuron, times this, or not times, with this weighted sum inside it. And so I'm going to have some sum over the number of outputs in the layer before that, the K minus first layer. So I'll call that R, and I guess to keep consistent, I'm going to make this a superscript, but if you like it as a subscript, then that's fine too. So this is the number of outputs in the K-1 layer. And in my notes, I wrote L equals 0 here, but knowing me, and I don't know off the top of my head if that should be a 0 or a 1. And if I thought about it, I probably could reason through it. But on Zoom, that part of my brain is not functional. So I'm going to leave it as L equals 0. But you guys are cleverer than me, and you might figure out that, oh, he actually meant L equals 1. Doesn't really matter to this discussion right now. But then this weight will be W L J K of O L K minus 1, where this O is the output L from layer K minus 1. So we're just focusing on a single neuron in layer K, the jth neuron in layer K. The jth neuron in layer K could be connected to any of the neurons in the previous layer, K minus 1. And so all of those neurons I'm representing here as O, output, and then each one of those gets weighted in the jth one. And so those weights potentially could, I guess, be 0, but those weights we're allowing to freely move. And then we're summing all those things together. So just recall that that's what's going on at a particular neuron in the kth layer. So I am just going to introduce I'm going to call this thing xj superscript k. It's just the sum. So I guess I can let's just say it's defined as the sum from L equals 0 to RK minus 1 of the thing that's above. So it's just the sum. And so now with that definition, I can use the chain rule to break this thing apart. And so I can say that the partial derivative of the loss function with respect to this weight that I'm focusing on is just the partial derivative of the loss function with respect to this particular activation function times the partial derivative of the activation function with respect to xjk, then the partial derivative of xjk with respect to the partial derivative wijk. So it's a lot, but that sandwich is just the exact same thing. What's on the left is equal to what's on the right. It's just the chain rule. Just taking the partial derivative of functions with respect to their arguments, and then arguments with respect to their arguments, and then eventually arguments with respect to their variables. And when I break it up this way, then it reveals that for one, this thing here, the partial derivative of this xjk with respect to wi or wijk, well, that whole thing, that is just equal to the output I in the k minus 1 layer. And this thing here, the partial derivative of the activation function with respect to this, I'm just going to abbreviate as a prime with respect to its argument, xjk. So I don't know that without knowing exactly what activation function you used, but I can solve for that. If it's a sigmoid or whatever, I just take the derivative of a sigmoid. I can plug that thing in. And then so what's left is this point right here. And all I need to do there is figure out how to take the output layer and push it back into all of the other layers. And so this is where the magic happens. And this is where we will pick up from next time. I'll put next time here. And then we can also talk about some of the more exotic neural networks getting outside of feed-forward and how to train them. So are there any questions here? Because now we're at 4:20. All right, great. All right, so hopefully that's review for some of you and interesting for the rest of you, and the ones who did review from, hopefully it's not too boring. Unfortunately, I have to move my office hours today to Thursday. So instead of having office hours on Monday and Tuesday this week, I have them on Tuesday and Thursday. I posted that to one of my classes, and I just realized now that I didn't post it to this class, so I apologize for that. But I can hang around for a few minutes if anybody does have any questions. I've been grading the submissions of your projects, and so some of you should already have grades for those. For the ones that were turned in closer to the due date, then you may not have grades for those, but I'm basically just spot checking right now. I'm looking forward to seeing your kind of full proposals. So with that, anybody wants to stick around for the next couple of minutes for questions? I have to take off at 4:30 here, but the rest of you feel free to pop off.
Sir, I have one question.
Uh-huh.
I have seen this gradient-based approaches used in most of the neural networks nowadays. And since we are learning this class, why are nature-based algorithms not that famous as the gradient-based approaches?
Well, I mean, Oh, you mean, oh, like why are meta-heuristics not you? I think that's an excellent question. Um, this approach was kind of it made a lot of sense for people to try initially when they started training these neural networks, because it was kind of easy to wrap your head around, and you knew that it worked for a wide range of problems. And then when people tried them, I think everybody was surprised at how well gradient descent um, worked, especially with and how easy it was to apply with backpropagation, as we'll kind of see next time, to see, like, exactly how the whole thing fits together. There now is some skepticism that these gradient-based approaches are actually finding really, optimal solutions, as opposed to getting stuck in local optima. But stochastic gradient descent seems to be, where basically you add a little bit of noise to the update rule that we have here, seems to work pretty darn well too. So I guess the reason why the genetic algorithms and so on haven't caught on is for simpler problems like these multi-layer perceptrons that are all feed forward. This just works so darn well. Now, for recurrent neural networks, you can still use this, but it gets a little uglier. And so, and then coming up with these topologies when you're at these fully connected neural networks, it's sometimes people are less confident that this is working well. So there's a lot of room for the nature-based meta-heuristics to come into play, but they also have to beat the success of these things and the simplicity, and that's kind of the major barrier.
Right. Thank you.
Mm-hmm. All right, any other questions? Good, all right. Well, in that case, I'm gonna end the meeting now, and I will see everybody on Wednesday, or on Tuesday if you come to office hours.